In this video, we're going to be learning about inverses of functions. We're going to start off looking at what it looks like in graph form. So if I have a function, we could call it f of x or just y equals. Those are the same thing, remember? Let's say negative 2x. So to graph a linear function, we use our y-intercept. So if it's not there, it's just implied that it's 0. So if we start at 0, we use our slope to find our other points. Our slope is negative 2. So we would say negative 2 over 1. That means we would go down 2 and over 1. And we'll just graph a bunch of points here. Let's go the other direction, up 2 and over 1. Alright, so there we got a nice linear equation, a nice line, has a negative slope. I'm going to show you what an inverse looks like. An inverse is really a reflection, and a reflection not across the y-axis and not across the x-axis, but actually it's a reflection across this equation, which is kind of a strange equation there. See if I can change colors here. So if I graph this is actually the line we reflect across. So let's find out what this line looks like so we can do our reflection. The slope is implied, it's just 1 over 1, and our y-intercept is just 0. So we start at the same spot, but now we go up 1 over 1. Up 1 over 1. So when we reflect for inverses, we're actually talking about reflecting across that diagonal line there. That line represented by this equation. This is our reflection line for inverses. So if I reflect all of my points across this line, then I can find the inverse function. So I'm going to change colors one more time here. Oops, I didn't want that one. So let's look at this point right here. Well, if I reflect it, it really stays at the same spot. So let's choose a different point. Let's go to the next one, this one. So if I look at my line, how far away, what's my run up to that line? I'm 1, 2, 3 away on my run. So the inverse would be the opposite, so I'd be 3 down from this line. So I would be talking about my rise instead. So 1, 2, 3 is going to be the reflection of that point. So it's really what I reflected right there. So this point got reflected across that line and it showed up on the opposite side. Let's reflect this point. So I'm the same amount run away from the line as I am on the reflected side, comparing my rise value. So I'm 1, 2, 3, 4, 5, 6 away run-wise, so if I reflect it, I got to be 6 down from my line. 1, 2, 3, 4, 5, 6. So there's my, again, my reflection happened right there. I ended up right there. So let's keep going, maybe one more here. Let's talk about this point down here. What's its reflection here? So if I'm 1, 2, 3 away from that line right there, rise-wise, and let's reflect it and talk about the run. 1, 2, 3 this way. So then that ends up being my reflection. So what is the slope of my inverse line here? I'm actually going across or running 2 and rising negative 1. So I'm a negative 1, 2, down 1 over 2, down 1 over 2, down 1 over 2. So I'll just put one more point there, that way we can draw this line. And my blue line is talking about my inverse now. So what's the equation of that line? Well, we already got the slope. And the y-intercept is 0, so this is really my inverse. and we'll get to this in a sec, but this is my notation for inverse. So as you can see, the inverse is related there. There's a good relation there that we could see. We're going to talk about the algebra in a sec here, how we get both equations if we don't graph. But really, just visually, draw this line again too. So the reflection is not all that obvious, but if you compare the points, that's really what is getting reflected, and those points are reflected across that line. So graphically, that's what inverses look like. We could graph the inverse. Also in your XY table, our values get swapped, and we'll talk about that right now. So let me get rid of this window. So we had y equals negative 2x, and if we use just a table of values, here's some possible inputs. And if we run that through the function, what's our output? So if I plug in negative 2 and substitute it in for x, what do I get? That's my output. So negative 2 is substituted right here. I have negative 2 times negative 2, that gives me positive 4. Do the same thing with negative 1. Now negative 1 instead of x. So negative 1 times negative 2 gives me positive 2. If I substitute 0, I should get 0. 1 in place of x would give me negative 2, and 2 in place of x would give me negative 4. It's essentially what we just graphed. It's exactly what we just graphed. But then we had our inverse, and we said that was negative 1/2 x, right? And let's do the same thing. Use the same values. Hold on a sec. Let's not use the same values. I want to talk about what happens in inverses of tables. So actually what ends up happening is the x and the y values get swapped. So instead of using negative 2 as my input, I'm instead going to use 4 as my input. And when I input that, I should get what started as my input but is now my output. I should get negative 2. So the values get swapped for inverses of functions. The x and the y values get swapped. Let's see if that holds true. If I plug in 4 for x, I have what's half of 4, that's 2, times a negative, so I get negative 2. And it actually works for all of our values. So instead of y being the output, it's going to be my input, and instead of negative 1 being the input, it's now going to be my output. So all of our values get swapped. And that actually is what we just graphed for the inverse, our blue line. So table-wise, our values get swapped for inverses. Graphically, they get reflected across that diagonal line, y equals x line. And so let's keep going. Let's do one more little case where we actually do the algebra involved. Also, before we get any farther, this little notation means inverse. So anytime you see this negative 1 above your f or the name of your function, it doesn't mean the same thing a negative exponent means, because it's not really in the spot where a negative exponent should be. If I wanted a negative exponent of a function, I would put my negative 1 over the x, not over the f. So this would count as a negative exponent, and I would apply my negative exponent properties. But this is just the notation for inverse, so don't get the two confused. Whenever you see the name with the negative 1 exponent, that is talking about what's the inverse of that function. Alright, so let's do the algebra now. And use the same example here. Negative 2x, and I want to know what my inverse is. We could actually match our notation here. That might help a little bit. So I have a function here. It's negative 2 times an input. That gives me my output. I want to know what the inverse is. Algebraically, what we do is we swap x and y, just like we did in our tables. So instead of y equals negative 2x, I'm going to swap x and y. So now I have x equals negative 2y. So all I did is I exchanged my x and y, put them in opposite spots. So that's my first step. My second step is to solve for y. That's what we always want functions to be in relation to. So solve for y. So if I wanted to solve for y, I would divide by negative 2 on both sides. Remember there's a little implied 1 there. Cross those off so we get y by itself. And on the other side we have essentially negative 1/2 x. And that's what we've been dealing with. We saw it graphically. We saw it in our table. And this is how we do it algebraically to find the inverse. So all we do is we swap x and y and we solve for y and we get the inverse function. Now we could use our xy table to graph it if we needed to. But for the most part, you'll see problems that just ask you for the inverse of the first function to give you. Alright, let's talk about one other way that we can kind of work with this. If I want to prove, if I'm given two functions, let's say I'm given 2x minus 4 is one function, and I'm told, supposedly, that its inverse is 1/2 x plus 2. You're going to see problems where you have to check or verify that these are actually inverses of each other. In order to do that, we do this trick right here. I could also call this g. Let's call this g of x. And then I talk about it this way. If I plug in and use composites here, if I say f of g of x, I should actually get just x when I actually do the composite and simplify. And then when I do the opposite, if I do g of f of x, I should actually get the same thing as well. I should actually get x. So this is one way that we check. We check these two composites, and if we both get the same answer out of them, we know they're inverses. So let's try that. Let's do f of g of x. So I'm going to plug this all in and input it into my x for f. So I have 2 times 1/2 x plus 2, substituting my functions there. Minus 4. What happens when we distribute here? 2 times 1/2, well, what's 1/2 of 2? That's just 1. And we got our x there. 2 times 2 would be plus 4. If I subtract 4, I get 1x. Well, that's what I wanted. Good so far. Let's check the other one, the g of f of x. So now I'm going to start with f of x and plug that function into my input for g of x. So I have 1/2 of 2x minus 4, and then add 2 to that and see what happens. So what's half of 2x? 1x. What's half of negative 4? Well, that's negative 2. If I add 2, I just get 1x. So doing both of them gave me x or 1x, so they are in fact inverses of each other. So that's how we verify that they're inverses. It's a good way to check. If you are looking for the inverse of a function and you do it algebraically, this is one way that you can check that you got the right answer. It's kind of a long way to check, but it is there if you want to be absolutely sure you got it right. So that's a good little intro to inverses of functions. We looked at them graphically. We looked at XY tables, and we also did it algebraically. So good luck practicing and finding inverses of functions.